Okay, the next chapter that we're going to get into is chapter 14. This is dealing with vibration waves. So a couple of things with vibration waves, we're going to have what's called periodic motion. Periodic motion is just any motion that repeats in a regular cycle. So an example would be, a pendulum from a grandfather clock or any kind of clock that has a pendulum. Another periodic motion is also a vibrating guitar string, or anything that or anything that goes up, bounces back and forth. Strings vibrate up and down usually. Springs would also be this periodic motion. So with periodic motion, we have what's called a simple harmonic motion. Motion that occurs when the restoring force of an object is directly proportional to the object's displacement from equilibrium. Now, along with this movement and everything, we're going to have a period, which is indicated with capital T, and period is just a time measurement. So, period, time needed for an object to repeat one complete cycle of motion. Now, we're also going to have this thing called amplitude, which is the maximum distance that the object moves from equilibrium. So, if we were looking at a guitar string, equilibrium would be when it is not moving whatsoever. Once we pluck that guitar string, then it starts to have that simple harmonic motion, and we can figure out the amplitude, how far away it's moving away from equilibrium. If we were to look at pendulums first, we can calculate out what is the period of the pendulum. So to calculate out the period of the pendulum, T, that would be equal to 2 pi times the square root of L over G. Now L is the length of the pendulum, and G, of course, is the acceleration of gravity. So let's look at an example of finding the period of a pendulum. So a pendulum with a length of 36.9 centimeters has a period of 1.22 seconds. What is the acceleration due to gravity at the pendulum's location? All right, so if we're looking at our formula, T is equal to 2 pi times the square root of L over G. And let's kind of put in the information that's given to us into our formula. T is the period, so 1.22 seconds is equal to 2 pi times the square root. Now L, the length is given to us in centimeters, but we need to convert this over to meters. So 36.9 centimeters to meters would be 0.369 meters over G, because that's our unknown. So we need to solve for G, and what I would kind of do first is get rid of that square root. And the way that we're going to do that is we're going to square both sides. So 1.22 seconds squared is equal to 2 pi squared times 0.369 meters over G. And then we need to get G by itself. So if we multiply both sides by G, 1.22 seconds squared times G is equal to 2 pi squared times 0.369 meters. Then we're going to divide both sides by the 1.22 seconds squared. I don't know why I keep on putting a 5 there, but it should be a 2. And that should give us our answer. So let's kind of see what that comes out to be. So 2 times 3.14 squared times 0.369. Divide that by 1.22 squared. I'm coming up with an answer of 9.78. That would be meters per second squared. And if you kind of think of the acceleration due to gravity, that's 9.8 meters per second squared. So we're not that far off what the acceleration of gravity should honestly be. Will it be really, really close? Yeah, it should be, but we might be off just by a little bit. All right, now, if we look at springs. So with springs, we have force exerted by a spring is directly proportional to the distance the spring is stretched. So the further out you stretch that spring, there will be more force. And the way that we can figure this out is by using what is called Hooke's law. Now Hooke's law is equal to force, that's equal to negative K times X. K represents the spring constant, and this depends upon the stiffness of the spring, and X is the distance the spring is compressed or stretched from its equilibrium position. So equilibrium position is when the spring is just there by itself, no force acting upon it. Now, before we kind of look at some more stuff, some springs do not follow Hooke's law. They won't bounce back. They're just, if you pull them too far, they'll just break. Now the ones that do are called elastic because they can bounce back and forth, and then eventually that will stop and go back to equilibrium. We have the same spring. What we can do with this is we can find how much potential energy a spring has. So the way that we find the potential energy, PE of the spring, is equal to 1/2 kx squared, which K still represents the spring constant, and X is the distance the spring is compressed or stretched, usually stretched. So let's look at an example with springs. So a spring stretches from 18 centimeters when a bag of potatoes weighing 56 newtons is suspended from its end. What is the spring constant? How much elastic potential energy is stored in the spring when it is stretched this far? Alright, so the first thing, trying to find the spring constant, so we're going to use Hooke's law. F is equal to negative kx. Now, what we can kind of do is just negate that negative sign because that's just reminding us that it's being restored. So F is equal to K of x. We have our force, 56 newtons. K is our unknown. X, well, spring is stretched 18 centimeters. And we have to convert that to meters. So K would be equal to 56 newtons over 0.18 meters. 56 divided by 0.18. And I'm coming up with right around 300 newtons per meter. And the spring constant, that's the units that we kind of use, newtons per meter. So that's the first part. So then the second part, how much elastic potential energy is stored in the spring when it is stretched this far? So we're trying to find potential energy, which is equal to 1/2 kx squared. Okay, 1/2 times K. So 1/2 K, 311 newtons per meter squared, times our distance, 0.18 meters. 0.5 times 311 times 0.18 squared. I'm coming up with a potential energy of 5.04 joules. Well, that should, just trying to figure this out. Yeah, that shouldn't be squared. It should just be newtons per meter. Don't know why I did that. Now, one other thing with springs is we're going to have this thing called resonance. Now, what is resonance? Well, this is small forces that are applied at regular intervals to a vibrating or oscillating object, and the amplitude of the vibration increases. Alright, so with a guitar string with resonance, once you pluck the string and you hear that sound just keep on going and going, is because that string is keeps on going up and down, back and forth, over and over and over, until eventually it will reach equilibrium. Alright, so this is section 1 of chapter 14. If you have any questions, let me know, and thank you for watching this video.